I went running this morning. God, it was beautiful. The full moon was out. And so I live in Houston, and it's a little more humid there than it was here this morning. So it really felt good. I was going to ask the mayor to do something about the hills, though. We don't have those in Houston. So, actually, I thought Wayne was going to introduce me. I guess the agenda got juggled.
No, I did it first. Wayne was one. Oh, and Mike was two.
I'm just glad it wasn't you, Pat. After I watch LA go through that. His knees were shaking a little bit earlier. Wondering what you were going to put up there. And to do that to an astronaut is quite an accomplishment. That's good. Hey, so, in thinking about the remarks for this meeting, I looked through the agenda, and more so than many of the conferences I go to, this one contains more participants in what Mike referred to as new space. So I was going to say something like, thank you for welcoming a large company like Boeing to the club, or something like that. But then yesterday I was talking to Jim McNerney, who's the CEO of Boeing, about our commercial space plans. And in his conference room, the boardroom, there's a picture of Bill Boeing right next to where the charts come up, kind of behind the podium. And it's one of those pictures that the person in its eyes look like they're looking at wherever you are. So it's a great portrait. He's standing there with a seaplane, one of the early Boeing planes that flew airmail. And the thought occurred to me that I should welcome everybody to the club. Yeah. That's kind of how Boeing started, and so it's good. Anyway, it's good to be here. This is a great crowd, and some fantastic topics get discussed, and so it's just good to participate. I think these conferences are great, but I kind of wish I'd see some more new faces in the audience. I think we need to get the messages that we have out beyond ourselves. The American public supports our space programs, but I think they quickly forget, in the midst of everything else going on, like government shutdowns, what's happening in space and the support that we need. I'm going to talk today about a topic that's near and dear to my heart, and that's the space station. I started working on space station in about 1986. I remember that because it was right after the Challenger accident. And I worked as a test engineer. I've been to several sites: Huntington Beach, Marshall, Johnson, KSC. I got to lead the team that finished the manufacturing and test of the first U.S. piece of space station, Node 1. And then eventually became the program manager. Gerstenmaier was my counterpart at that time. That was a real learning experience. And now it's part of the portfolio that we have in space exploration. So I have a real attachment to space station. Right now it's key to sustaining the U.S. presence in space. It's key to fostering the development of commercial cargo and crew industry, serving as kind of the foundational tenant or foundational customer. It's extremely important as a scientific laboratory, and there's some really good science coming out of station. I'll show a few examples of that. It's a place where we can prove the technologies that are going to be needed for going beyond low Earth orbit, so we can test those out before we count on them for our missions. And it's a place where humans like LA and Sandy and others can learn to live and work in space. So it's really kind of the heart and soul of what we're doing in space right now, and the jumping off point for things that we want to do in the future. ISS it's an amazing machine. It just really is. It's the largest, most complex international scientific project in history, and it's our largest venture in space to date. It was designated as a national lab in 2005, so it's a research outpost. It's, as I mentioned, a test bed for future technologies, advanced industrial materials, communications technologies, medical research, and a lot more. It's a test bed for building and maintaining large structures in space, and I'll talk a little bit about what all that was involved in that as we go forward. It's been a model for international cooperation. international cooperation was one of the main reasons that funding was able to be sustained for space station through its life. It's, I'll always remember the first time. The space station processing facility was a huge empty building for a while after it was built. And the first thing that came through there was the docking module for the Mir space station. And the Russians came over from Russia. They set up their test equipment, plugged it into their docking module, laid their drawings out, and started testing. And all of us Americans who were here and had never met Russians, I remember standing in this cupola that overlooked the high bay and just watching with curiosity, as how this new culture or different culture was going to work. And after we worked with those folks for 2 or 3 weeks, it became apparent that they were just like us, right? They had daughters and didn't like their boyfriends. They had all the same problems that we had. And so, but learning to work in those cultures was really important. Another experience I remember is sitting at a conference table, and there were all Russian engineers down one side of the table and U.S. engineers down the other side of the table. And it occurred to me that many of those folks had grown up designing intercontinental ballistic missiles and pointing them at each other. And here they were sitting at this table trying to build the station together. And it wasn't just the Russians. The Japanese are a very different culture. The Europeans are different as compared. So the effort to get all those cultures working together was as significant, almost, as the technical challenges of building a station, and something certainly that I believe will need to be leveraged as we continue exploration beyond low Earth orbit. And the station received the Aviation Week Laureate Award for Space in 2010, and the write-up said, "It's arguably the signature engineering achievement for the last 60 years. By working together, partner agencies demonstrated that the station is as much an achievement in foreign relations as it is in aerospace engineering." And I think that's definitely true. There's been some real benefits to humanity, and I'll talk a little bit more about it on the following slide, but just kind of starting at the top and going around counterclockwise. Paige Nicholson is talking about where the robot entered her head. She had brain surgery. She was the first patient of a system that was based on the technology from the robotic arm on station. Unique about that system is it can operate in an MRI, so the docs don't have to take it from the MRI back to the operating table and make and it also has some collision avoidance software that's part of the system that helps the surgeons navigate through the brain and avoid places they don't want to cut. So it's made a big difference. Vaccine development, next picture down, for whatever reason, we haven't figured it out, but there's the virility of viruses increases in zero gravity, and that has allowed studying more mutations and developing vaccines for things like salmonella. Earth observation can be done from station. And then there's been a treatment developed for Duchenne's muscular dystrophy, and again, I'll talk about that on a chart that's coming up. And then from the top, moving clockwise, developing capabilities to go beyond low Earth orbit, just learning to live in space for long durations, the life support systems required, and the materials that are required to do that kind of activity, all being proven out on station. Next slide, please. So here's just some facts and figures about station. It's over 32,000 cubic feet of pressurized volume. That's about the equivalent of a 6-bedroom house. So large space inside. Weighs nearly 900,000 pounds, so massive in that regard too. The solar arrays, the surface of those solar arrays is about 9/10 of an acre. And just to put that in perspective, that would cover 8 basketball courts if they were all put together. So they're huge. Crews have eaten 25,000 meals since the first expedition in 2000. It travels a distance every day, just about every day, equivalent to the moon and back. So it's zipping around. The water recovery system on station recaptures reduces the dependence on delivered water by 65%. So we need, instead of a gallon a day, 0.34 gallons a day for the crew to work. For every gallon, we only need 1/3 of that because of the recovery system. There's about 350,000 sensors 350,000 sensors that are monitored by 52 computers and 1.8 million lines of code, so a pretty complex computer system on board. There's been more than 115 space flights that were required to construct station. Then the truss, this picture depicts that the truss is 3 feet short, 357 feet of being as long as a football field, including the end zones. So just a really very large, massive, complex machine. And when we put it together, it was the first of a kind, one of a kind, and had to work when it got on orbit. One of the biggest challenges we faced building the station was the pieces never saw each other until they were on orbit. Some pieces were still in preliminary design while other pieces were flying. And so the whole activity of verifying that on the ground so that when you plugged it together on orbit it worked was a real challenge. I used to tell the story of I couldn't even hook up my stereo system and turn it on and have it work the whole time. But most people today don't remember those stereo systems. You just buy a box and turn it on today. So how did we do some of that? Next slide. We don't always think about all the stuff that happened on the ground before it went on orbit. All those pieces were seeing each other for the first time on orbit. And we did some amazing things in space, but that meant we had to do some amazing things on the ground first. One of the big tests we did was called the multi-element integration test. And that's the bottom left picture there. We couldn't put all of the station together on orbit, but there were tests where we put representative pieces together on the ground, verified the interfaces, and although we couldn't actually mate them, we had jumper cables that put them together. And that way we found things on the ground before we got to orbit and were able to fix them. The next slide shows the choreography of the station going together. Here we go. So the first piece that went up, of course, was the Russian module, and then the first U.S. piece was the node. I'll just let this go through here, and you can watch it. It describes the different pieces, labels them as they're coming up. There were 18 major U.S. components. The last U.S. component that went up was the starboard 6 truss segment, and that was delivered in 2009. You'll see that as we get to the end here. It's been continuously staffed since 2000, so there have been people on board station for nearly 13 years now. And when those people, the first crew, Shep and the crew that went up first, it was just the early version of that. So, one way to describe it is like building a 6-bedroom house, building the first room, moving a family of 3 in, and asking them to finish building the house while working full-time from home. So it was kind of an amazing task to put this all together. I think something that gets left out of the discussions that we have on exploration architectures. Sometimes we talk about whether we need a big rocket to launch pieces into space for exploration. And I think we leave out of those discussions the difficulty of assembling in space. And if we don't have a big rocket and we need to kind of repeat some of the activities associated with station in order to assemble an exploration vehicle in space, the cost and complexity of doing that needs to be considered as part of those discussions, I think, going forward. Okay, so there it is, a beautiful thing. Next slide. Hey, I wanted to talk about some of the medical discoveries that are happening on station. So it plays a critical role in support of the nation's space exploration and supports a variety of pure and applied research for the United States and its partners. During an average 6-month period on station, as many as 200 investigations operate, and between 70 and 100 of them are new each time as they're done. There are close to 600 journal articles that have been published on the research, and currently an average of 35 hours per week of crew time is spent on this research. So I mentioned Duchenne's muscular dystrophy. Many diseases are caused by proteins in our body. We grow protein crystals to design drugs that can attach to those crystals and inhibit them in our body and prevent the disease. Some of those crystals aren't perfect enough when we grow them on the ground to really see the crystalline structure. So the particular crystal for this disease was grown on orbit because of no gravity. It could be grown more perfectly. And it was discovered in that crystal grown on orbit, not seen in one grown on the ground, a water molecule that happened to be key to designing the crystalline structure to wrap itself around the protein crystal and inhibit this disease. So that, having seen that crystal, the treatment has been developed on the ground now, and it's being tested in Osaka, Japan, and hopefully we'll be able to treat this disease. 1 in 3,000 U.S. males get this disease, and their life expectancy is only 25 years old. So it's a really nasty disease, and if that's the only thing, a cure for that is the only thing that comes out of station, I think it's been worth what we've done. Another one shown on here is bone loss. So bone loss is a big deal in space. As the crew's exposed to reduced gravity, their bones atrophy, and treatments have been developed to help the crew on orbit combat that. And it turns out those same treatments are useful in treating osteoporosis and other diseases on the ground. So already being offered in the commercial market, these drugs represent a $1.2 billion per year industry that has morphed out of the research done on space. Another example here is this kind of tube thing with the purple light in front of it is an experiment in plasma and researching complex plasma on orbit. Some really good things were discovered in the research, but it was also noticed that this device, when passed over a petri dish of the bacteria that causes staph infection, killed all the staph infection after an exposure of about 30 seconds to the plasma that comes out of this device. It's now being used to treat wounds. If it's passed over a wound, it heals better. And we'll continue to more research on how it can be treated or how it can be used in treatment of staph. So it's an example of something that was kind of an adjacent discovery. So there are focused outcomes. When the research was done for the Duchenne's muscular dystrophy, that's what it was trying to find. There's collateral outcomes like bone loss. We were doing research to counter a problem on orbit. It could also be used on the ground. And then there are unexpected outcomes like the one I just described with the plasma experiment. All those are happening on station. Next slide. The next area to really think about is fundamental research that can be done on station to develop the technology that we need for exploration beyond low Earth orbit. So it's a proving ground for that activity. A few examples. The first one in the upper left is the NASA docking system. It's a new docking system that will be kind of a universal docking system used by all participants in exploration. And it's going to be attached on the station, and the commercial crew vehicles will be the first users of that system. And then it will be applied to Orion and other vehicles and create a system where we can dock on orbit with systems from all countries successfully. Moving across the page there is a map of the current ECLS system. So testing out environmental control systems, making them more closed loop, is a real important thing that we can do on station. There's a lot of rotating machinery, pumps, fluids moving around, and they all behave a lot differently in zero gravity than they do in any kind of test facilities we can put together on the ground. So proving the reliability of these systems on the station before we depend on them for trips to asteroids or to the moon or to Mars is very important. Lots of, in the lower left, experiments done to validate that materials can survive in space, and so we expose them to space on station and see how they behave as we develop materials for exploration. And then learning to work with robots in space as we go forward in exploration, that will be key. And so work's being done on station in that regard. Next slide, please. And then finally, just living in space. You know, in LA and Sandy have certainly had experiences with that. But learning how to live, how to stay healthy, and how to be productive in space can be done on station so that we know how to do that when we go on the long-term missions. There's an experiment being done where Scott Kelly and one of his colleagues from Russia are going to spend a year on station. The interesting thing about Scott doing that is he has a twin brother, Mark, who will be on the ground kind of as a control subject, and they'll be able to compare how the two of them, how Scott's the one on orbit, right? Okay. How Scott and Mark compare with one being on orbit and one being on the ground as they go through. So it'll be a good test as we go forward here. Okay, now I want to talk just a little bit about access being key to this. So if we're going to continue station, we have to make access more routine and more affordable. And the real key to that is commercial cargo and commercial crew. So there are two providers now for cargo, SpaceX and Orbital, and that's great because we need to increase the amount of supplies, experiments, and ultimately people to ISS. So continued success of that's really important. Proving out new technology and science quickly by using the ISS can reduce cycle times and therefore costs for many advances that improve life here on Earth. Because the access is cheaper and more frequent, the barrier to entry is lower, allowing more creativity and opportunity for crossbreeding of science and technology applications. When I grew up in Fort Myers, Florida, that's where Thomas Edison's laboratory was. And there's two things I remember from that laboratory. He tried thousands of different filaments in light bulbs before he found one that worked. And so if we're going to make good discoveries on station, we have to have a capability to do hundreds and thousands of experiments such that we can achieve the results that we're looking for. The other thing I remember from that laboratory is there was one thing he discovered totally by accident. There's a glob of rubber on the, Harry Firestone was his neighbor down there. And there's a glob of rubber on the floor that the technicians spilled sulfur into as they were doing experiments with rubber, and through that total accident discovered the process for vulcanizing rubber that Harry Firestone turned into a pretty cool business. So that happens by more research, more opportunities to get into the lab. And so that just the access and the ability to do experiments is going to be very key to the amount that we can learn from station. Scientists, maybe they have a great idea in the middle of the night and they want to go try it in the lab. Waiting 5 years or 10 years to get that experiment on orbit makes it difficult to have research lead to results. And so, again, proven access is just absolutely important as we move forward. Okay, next slide. This shows the other part of access, which is commercial crew. And of course, we're all excited about that coming to fruition as we move forward here. I'll move just one more slide. This shows, John Mulholland's going to talk more about CST-100 and Boeing's involvement in commercial crew on the next panel, actually, that follows me. I often kid John, if you had a chance to meet him here, that he's not a rock star like some of his peers. He's not quoted in the press every other day, and he's not been in a movie, at least yet. But I don't know of anybody that's more qualified kind of to look across Boeing and pick out the innovations and pass those innovations through a filter based on the years of experience John's had leading programs, taking humans into space, shuttle in particular, and focusing all that in the development of a safe and reliable vehicle. Frankly, sometimes it's a little frustrating that folks in the business are talked about as innovative almost in juxtaposition to Boeing. And I don't think that's the case. There's a tremendous amount of innovation across the company that John's tapping into. Things like, and he'll show you some of this, I hope, the spun-form pressurized vessel that doesn't require welds, that was developed from the guys that do spun-form domes for the top of tanks on rockets. The automated rendezvous and docking system that was proven on Orbital Express, and John's applying that to commercial crew. We reached out and got the lighting out of commercial airplanes. If you've been in a new 737, it's got the lighting, but that lighting is designed to give an impression of more spaciousness and to relax the passengers. And that can be a cool thing, I guess, if you're flying in a small capsule. The panels in our capsule are being designed by the guys that do business or build those panels in the helicopter business. And training's being done by the training systems guys. So John's really reaching out, pulling all that innovation in. And I think that's what this whole program needs to be about as we strive to make safe and reliable more affordable. So anyway, John will talk more about that on the next panel. Maybe the most innovative thing he's doing is his team is only 350 people. And that is really an innovation compared to the programs I've been involved in the past, to be able to move a design through the critical design review with that size team is just amazing. Next slide, please. Hey, if we're really going to get the affordability and access down, we need to have more destinations than this International Space Station. So these are some that are out there. And I think the business model that Bob Bigelow's put together is really exciting. Having as clients countries that want to have their own space program, but maybe can't afford the infrastructure associated with putting their whole program in place, but they certainly have the resources to lease space for some period of time on one of those modules. A couple years back, we went to the Farnborough Air Show with Mr. Bigelow and met with several of his potential customers. As an aside, it was really interesting to hear them talk about their country wants to do space because it's inspiring to their youth, it advances their technology, improves their economy, and somehow we've forgotten that a little bit in this country and need to take a lesson from those folks. But anyway, I think as we move forward and access becomes dependable, the price of it goes down, it will be a chicken and egg thing with more destinations coming into being, and certainly looking forward to that. The next slide, so where are we going next? What are we going to do with this? Station certainly is the foundation for a lot of technology and knowledge that can be applied to doing a lot of things. I think Mars is the ultimate destination. There are several paths being debated for how we get to Mars. But they all, we need to find the commonality of all those and work on advocacy of them together. Next slide. I just want to leave this slide. This is kind of what it's all about for me, is all the stuff we do is inspiring. I bet everybody in this room has a story about getting involved in this business because something they were inspired by. Inspired many of us to study math and science. Many more of us actually than ended up working in space, so it works in all industries. And we just need to keep a focus on that. So ISS is laying a great foundation. It's showing us how to do construction in space. It's a catalyst for international cooperation. How do we live and work in space? The technologies required to go beyond low Earth orbit. It's maintaining a human spaceflight presence at the moment. It's a catalyst for development of private industry providing transportation to low Earth orbit. And it's producing incredible science that's leading to benefits here on Earth. We need to band together to garner advocacy for going beyond ISS. Public, congressional, administrative support is more factioned than I think it ever has been. And to do that, we should all join forces and not talk about this or that, but talk about how all these capabilities combined can provide us the capability to continue our exploration. And finally, I think we need more discussion of why we do this and maybe less of the capabilities that exist and debates around those capabilities. So if all of us can just get a few examples of the good things that are coming out of human spaceflight that are helping on Earth, creating benefits for humanity, the pure science it's leading to, and focus on advocacy from that perspective, I think that will align the forces and allow us to continue as we go forward. So thanks for the opportunity to talk about Station a bit, and I think I have a few minutes left. I can answer questions if there are any, LA.
So we have quite a few interesting, some challenging questions for you. One is if you sit in a unique position in that you have the commercial crew portfolio as well as SLS. Obviously, those in some ways fight for a slice of the same pie. So what are your talking points in order to get folks to not argue over how big their slice is, but rather get a bigger pie?
Yeah, so the first thing I think it's important is to look at it's like a three-legged stool, I call it, that NASA has laid out for our path forward. The first leg is ISS and keeping it going, and as I mentioned, all the benefits that come from that. The second leg is, in order to keep ISS affordable, we need commercial cargo and crew to reduce the cost of resupplying station and allowing that to continue in such a way that there is room in the budget for programs like SLS and Orion to take us to the destinations beyond low Earth orbit. So it's important to look at all three of those things synergistically, complementary, and not as opposed to each other. I think the argument to increase the top line, which is kind of what that question was getting at, is one that we all just need to join together, as I mentioned, and not tell the integrated story, not advocate in competition with each other, but in support of each other, and ensure that there is support for all aspects. And then, there's just work to be done to educate the public and Congress and staffers in particular about the benefits that come out of space, so that the top line can be increased.
The next question is about the first leg of the stool, the ISS, and I think not only for the reason you state there, but also for commercial crew to be really a viable program, you sort of need to extend it beyond 2020. What do you see as the major challenges in doing that?
Well, I'd say, yeah, it's important. I mean, we've done the work to show that it can certainly survive as a machine through 2028. The question is, can it survive politically through 2028? And that's the work that we're doing now to generate advocacy. If we're going to get good science out of station, first point, if we're going to get good science out of station, it's got to have a longer horizon than 2020. We'll be shortly to the point where scientists won't be interested in developing experiments to do research on station if it doesn't have a sunset that is greater than 2020. And so we need to do that. Mike Griffin made a great comment, I thought, at the Naval Academy on the panel we were on next week. Said, we never build a laboratory of any significance and say, okay, we're going to operate this for 15 years and then we're going to close the doors. We operate laboratories and facilities like that as long as they're returning a benefit and are useful. And that's the way we need to look at Space Station going forward.
During your talk, you mentioned how a lot of what we're learning on ISS has applicability on Earth. And this question's about, can you talk to how living off the grid on ISS with closed-loop recovery systems can apply to sustainability here on Earth?
Yeah, there's two examples pop into mind. There's been a lot of work done with the water purification systems on station and that technology being applied to third world countries where pure water is a big deal, and leveraging that to help those folks. Another one that comes to mind is there's been a lot of work on station, perhaps you did some, to use a kind of a sonogram system to investigate different conditions within the body. And that can also be used in remote places on Earth to send that imagery to an emergency room in a hospital, and the docs there can interpret it and help medical technicians in more remote places give care to people. My favorite example of it is the Detroit Red Wings have one of these machines in their locker room, and if one of the hockey players get hurt, they check out his knee and they link it to the hospital, and the doc can decide whether they need to go in for knee surgery or tape him up and get him back in there.
Okay. I think we're out of time. Let's thank John for his wonderful presentation.